Hi, welcome to How Not to Use Statistical Significance. In this video, we'll be talking about ways that people frequently misuse or misinterpret statistical significance. While statistical significance is an immensely useful tool in reporting and interpreting scientific results, there are misconceptions about it that sometimes cause confusion. We'll be trying to clear some of those up in this video. In this video, we're going to assume that you already know at least a little bit about hypothesis testing and two related tools, statistical significance and p-values. We'll assume, for example, that you know what the definition of the significance level alpha is. If you're not familiar with these topics, you may be interested in the video Statistical Significance and/or the video What's a P-Value, both available on this channel. For simplicity, when we show examples in this video, we'll assume Gaussian errors and use two-tailed hypothesis tests, significance levels, and p-values. The same statements hold for one-tailed tests as well. If you'd like to know more about one-tailed and two-tailed tests, you can look at the videos mentioned above. Okay, let's get started. First, let's talk about the choice of significance level alpha. The significance level is the chosen benchmark to decide if a result is statistically significant. If the p-value is less than alpha, then the result is defined to be statistically significant. A very common choice of the significance level alpha is alpha equal to 0.05. Let's say we're measuring some quantity Q. The null hypothesis predicts the value Q0 for Q, shown here by the red arrow. Our alternative hypothesis will be that the true value of Q is some other value not equal to Q0. Assuming the null hypothesis, and assuming Gaussian errors, the measured value Q measured will be Gaussian distributed around Q0. The Gaussian has a standard deviation sigma q equal to our measurement uncertainty. 95% of measured results Q measured will fall within about 1.96 sigma q of Q0, so within the blue band on the plot. If we choose alpha equals 0.05, any result Q measured falling outside this band will be considered statistically significant and will cause us to reject the null hypothesis. The choice alpha equals 0.05 is so common that many people casually use the term statistically significant to refer to results with p-values less than 0.05. However, it is important to realize that even in situations where the null hypothesis is true, p-values less than 0.05 are not that rare. Let's assume for the moment that the null hypothesis is true. There is a 5% chance that your measured result Q measured will fall outside of the blue band. In these cases, you reject the null hypothesis, even though it is true. So using alpha equals 0.05 in 1 out of 20 measurements where the null hypothesis is actually true, you will reject it. Often, if the null hypothesis is rejected by a measurement, people will take this as definitive. They think that the null hypothesis is definitely not true. So here we see one mistake that people often make with statistical significance. They interpret the rejection of a hypothesis as definitive when it isn't. This is especially important for large values of alpha, like alpha equals 0.1 or alpha equals 0.05. It's a valid choice to use a value like alpha equals 0.05, but it's important to keep in mind that the null hypothesis will sometimes be rejected, even if it is, in fact, true. Now, taking the rejection of a null hypothesis as more definitive than it actually is an issue for any measurement. But it's particularly a problem if you make many measurements. For example, let's say you make 20 measurements and the null hypothesis is true in every case. Let's also say you use alpha equals 0.05. You should not be surprised if you reject the null hypothesis in error in 1 or even a few of your measurements. This is known as the look elsewhere effect or multiple comparisons problem. This problem can be partially remedied by reducing alpha. However, when reporting results, if multiple tests, in other words, multiple measurements, have been performed, one should report the results of all measurements, whether they were statistically significant or not. At the very least, one should report how many measurements were performed. This is also a problem if scientists or scientific journals think only statistically significant results are worthy of publication. For example, let's say 50 scientists each take a measurement of a different quantity. These scientists may be studying very different things. Perhaps they are even in different fields. Let's say they all use alpha equals 0.05. 5 of them obtain results that are statistically significant. They all report their findings. On the other hand, 45 obtain results that are not statistically significant. What happens if some of these latter 45 consider their results not interesting enough to publish? And note that we'll assume that all of these results were otherwise of publishable quality. Here, the look elsewhere effect has arisen again in a different context. Although each scientist only produced one result, not all of the scientists' results become publicly available. So there is a large number of results that the public doesn't know about. Now, even if the null hypothesis was true for every measurement, we would expect a few results out of the 50 to be statistically significant, just by chance. If many of the not statistically significant results don't see the light of day, then published results will seem more statistically significant than they would be if the look elsewhere effect were properly taken into account. So it is important to not ignore the existence of results which are considered not statistically significant. Next, let's say a scientist measures some quantity Q. They want to know if there is an effect which causes the true value of Q, Q true, to deviate from the null hypothesis prediction Q naught. Let's also say that the measured result Q measured is compatible with the null hypothesis prediction Q naught. So the result is not statistically significant. Does this mean that the null hypothesis is true? Okay, let's again take alpha equals 0.05. Let's imagine that Q measured landed about 1 sigma Q away from Q naught. So this is very compatible with the null hypothesis. However, the result is also compatible with other hypotheses. For example, here we could have an alternative hypothesis that predicts a value QA for Q located just to the right of Q measured. Or we could also have an alternative hypothesis that predicts this value QA for Q that lines up very well with Q measured. Now, the null and alternative hypothesis can't both be true. So if there are values of QA not equal to Q naught that are compatible with the measurement, then we have not proven the null hypothesis true. Sometimes people mistakenly believe that if they fail to reject the null hypothesis, this means that they have proven the null hypothesis. As we have seen, this is not the case. Next, let's think about a result that is determined to be not statistically significant. Does that necessarily mean that the difference between the true value of Q, Q true, and the prediction of the null hypothesis, Q naught, is too small to be important? Let's look again at the case where Q measured differed from Q naught by about 1 sigma Q. So the measured value was determined to be not statistically significant. We would suspect that this Q measured resulted from a Q true not too far from Q measured or Q naught. Here, not too far from means a distance not much bigger than the measurement uncertainty. So we have reason to believe that Q true is not too far away from Q naught. However, this doesn't mean that the difference between Q true and Q naught is unimportant. For example, if this measurement is of a medical nature, this difference could mean the difference of several thousands of lives. What it does mean is that your experiment can't establish the difference between Q true and Q naught. So if this difference is important, you might want to improve your experiment to reduce your measurement uncertainties. With a reduced error bar in a subsequent measurement, you may be able to reject the null hypothesis and narrow down the value of Q true. Okay, so we just saw that a result being not statistically significant doesn't mean there isn't an important difference between Q naught and Q true. Now let's ask a related question. If the difference between Q naught and Q measured is statistically significant, does that necessarily mean the result is important? Here we display a case where the difference between Q measured and Q naught is statistically significant. So Q measured is about 4.5 sigma Q larger than Q naught. We would suppose that Q true is in the neighborhood of Q measured. However, this just hints that the difference between Q true and Q naught is fairly large compared to your measurement uncertainties. That doesn't mean it is large enough to matter for some particular application that you have in mind. Okay, so we've seen from these last two examples that whether or not a result is statistically significant does not directly translate into whether or not the difference between Q naught and Q true is important. So it's important to keep this distinction in mind. Okay, let's summarize. Statistical significance is a hugely useful concept, but it should be used correctly. Here we've covered some misconceptions that people might have about statistical significance and some mistakes they might make while using it. Hopefully this will help with a better understanding of scientific results.